Hello. We were discussing reciprocal lattice vectors, and while discussing reciprocal lattice vectors, we defined B1, B2, B3, the axis vectors in reciprocal lattice. And we have also mentioned the condition that Bi dot Aj, where Aj are the real lattice axis vectors, this must be twice pi times Kronecker delta ij. So Kronecker delta ij, as you already know, equals 1 if I equals j, and this is 0. Sorry, it's 1 if I equals j. This is 0 if I not equals j. So we must see why this condition is necessary for the reciprocal lattice vectors. For our arbitrary function in R that we have considered in 3 dimension, we represented this as a Fourier series, and that was sum over G. These are the equivalent of translation vectors in reciprocal lattice, the so-called reciprocal lattice vectors. Ng, the Fourier coefficients, exponential of I G dot R. Now, if we consider a translation in real space, T equals U1 A1 plus U2 A2 plus U3 A3. If we consider this kind of a translation, then subject to this translation, our function in R must remain invariant. That means N R plus T must be equals NR. Now let's see what this quantity is according to this definition of the translation vector. This quantity can be given in terms of the Fourier series as sum over G Ng exponential of I G dot R plus T, which essentially becomes sum over G Ng exponential of I G dot R times exponential of I G dot T. This. And if this quantity has to be NR, that is given like this expression here. That's basically this part. Then this part has to be 1. In other words, in order to satisfy the conditions that we have laid down, exponential of I G dot T, this has to be 1, and in order to this be 1, we require G dot T, this quantity, to be twice pi m, where m is an integer. So this is the condition we have. How can we satisfy this condition? So how do we represent G in the reciprocal lattice? Just like T in the real lattice, we represent G in the reciprocal lattice as V1 B1 plus v2 b2 plus v3 b3. So with this definition of G, in order to satisfy G dot T equals twice pi m, this is the condition that we found to be necessary to have the periodicity in the crystal, we require that Bi dot Aj be twice pi delta Ij. If we have this condition satisfied, then we will have the boxed condition here implied from that. Okay, after discussing this much, we should now see how the diffraction takes place in a lattice. Earlier we have derived Bragg's law the way Bragg did it earlier, considering reflection from crystallographic planes. But in reality it's not reflection, it's diffraction. So we must see how the diffraction takes place and how we can understand the physics by working out the mathematics related to the diffraction. So we consider a crystal specimen here looking something like this of any arbitrary shape, and we consider some incident wave coming and falling here. It gets scattered, maybe goes along this direction. Incident wave comes like this, gets scattered here. Sorry, I couldn't draw it parallel. I want to make it parallel. Something like this. So this is the incident wave of the wave vector k, and this is the scattered wave of wave vector k prime, let's say. Here is the origin, and from this origin, this point of diffraction is placed at a position vector r. We consider a volume element here, like this, and we draw a perpendicular wavefront like this. So this angle must be 90 degree. Similarly, here we draw a perpendicular wavefront where this angle must be 90 degree. This volume element we call dV, and this is our crystal specimen. The incident beam may be represented with the waveform e power I k dot r, and the outgoing beam here that may be represented with e power I k prime dot r. And here the difference between k and k prime, so k is somewhere along this direction, k prime is somewhere along this direction. This vector is delta k. So k prime minus k, that equals delta k. So we consider diffraction of wave in this crystal specimen, as we can see in this figure, and the difference in the phase factors of the incident and the diffracted wave, scattered wave, that can be represented as exponential of I k minus k prime dot r. This is the difference in phase factor. Okay, and this is for the beams hitting at a distance r apart, separated by a vector r. Now the wave vectors of the incoming and outgoing beams, as we have marked here, k and k prime. So we assume that the amplitude of the wave scattered from the volume element here, dv, is proportional to the local electron concentration in the specimen. So if we have n as the electron concentration, it's of course a function of r. It's the local electron concentration. It's no longer the arbitrary function that we have considered in case of Fourier transform. So this is the local electron concentration, and when some photon gets reflected, scattered, it depends, its scattered amplitude depends on the local electron concentration in there. So NR is going to be important. The total amplitude of the scattered wave in the direction of k prime, that is proportional to the integral of NR, that is the local electron concentration, times this phase factor that we have considered. So the amplitude of the electric or magnetic field wave vector in the scattered electromagnetic wave is proportional to the integral of NR times the phase factor. So that thing we can call scattering amplitude. Let's go to a new page. Let's define this term, scattering amplitude. It's called F. So F can be given as integration dV, the volume element, in R, that is local electron concentration, times exponential of I k minus k prime dot R. This quantity, which if we write delta k for this, k minus k prime, can be written as this. So delta k measures the change in wave vector. So delta k is called the scattering vector. Now we introduce the Fourier components of NR. So NR is here the local electron density, but in a periodic crystal, it is also a periodic function. Therefore, the same kind of Fourier transform, Fourier series that we have discussed earlier is applicable for NR as well. Now if we write in R in terms of the Fourier series, we can write f equals sum over G integration dv ng exponential of I G minus delta k dot R. Let's discuss two situations. First, G equals delta k. If we have this kind of a situation, what do we get? You can clearly see that the argument of this exponential goes to 0 in this condition. And if the argument of the exponential goes to 0, the exponential gives us 1. So, in this condition, f will be nothing but total volume times ng. This would be f. And the second condition is certainly G not equals delta k. If G is not equal to delta k, that is if delta k differs significantly from any reciprocal lattice vector, then f becomes negligibly small. F is nearly 0 in this condition, and it's a homework for you to show this. Now, in case of elastic scattering of a photon, its energy is conserved. So its energy is h cross omega. That quantity is conserved. And the diffracted beam, let's say, has a frequency omega prime, which is c, that is the velocity of the photon, times the absolute value of k prime. And that must be omega because the energy is conserved, and this omega prime times h cross is the same as h cross time omega. So conservation of energy requires the absolute value of k to be equal to the absolute value of k prime, although they may be at different directions. That's allowed. In other words, k squared equals k prime squared. And we have earlier seen that for a diffraction pattern, a bright spot, we need delta k equals G for non-vanishing scattering amplitude. And if delta k is equals G, we can write k plus G squared of this equals k squared. Remember, delta k is nothing but k prime minus k. And we can also recast this equation in the following form: 2k dot G plus G squared equals 0. Now, if G is a reciprocal lattice vector, minus G is also a reciprocal lattice vector. Negative of G is also a reciprocal lattice vector, and we can as well call it G. There is no difference. Therefore, we can also write twice k dot G equals G squared by putting G equals minus G. And this expression is often used as the diffraction condition. Although every statement that we have here, starting from here, all these are diffraction conditions, this is particularly useful in many cases. Okay. In fact, from this diffraction condition, we can find out Bragg's law. So, your homework would be to to prove Bragg's law from the diffraction condition.